So if you turn your books to page 417, the final thing we're going to get into, I'll take my picture of the sea slug off. In the third type of phenomenon here, we're going to talk about something called long-term potentiation. Long-term potentiation. Long-term potentiation, for a definition, is something electrophysiological. It is electrophysiology. Does anybody know what that term means? How a neuron works. It involves action potentials and all that kind of stuff. The key area of your brain for memory appears to be what? What's the key structure that seems to be involved in memory in your brain? Is it the amygdala? No, the amygdala is emotions. The hippocampus. Does anybody know what hippocampus, where that word came from? If you ever play Trivial Pursuits, somebody looked at the hippocampus and the picture you have on 417 and thought that that looked like a seahorse. So hippocampus is Latin. Actually, it's looked like a seahorse, and that's why they called it the hippocampus. Kind of a weird thing. If you look in the picture on 417 with a little more detail, it doesn't look like they've really mapped out the areas of the hippocampus there. Yeah, what they basically have done in these types of studies, they've used rats. But what they do is they kind of take some cells out of the hippocampus. This will be important to note. They take cells out of the hippocampus, slices, if you will. And there are a few key areas you would want to know about here. There's the area called the dentate gyrus. Figure 9.38 might be the important one for you. The dentate gyrus. And what is the dentate gyrus connected to? What area does that go to? Actually, even the perforant pathway. So the perforant pathway going to the dentate gyrus, figure 9.38. Then it goes to what other two key structures do they? Just letters of the alphabet here. CA3 and CA1, tiny little fun facts that aren't really that fun. CA, they named them CA3 and CA1 because the term actually is corno-ammones, which also stands for seahorse. Which kind of scientist would be doing this kind of nonsense on us? Looking at brain structures and connections in particular areas. Does anybody know which kind of neuroscientist would be doing this kind of thing?
Neuroanatomist.
Bingo! This is very neuroanatomically based. Very neuroanatomically based. So this is the neuroanatomist, CA3, CA1. So you've got connections here. So that's kind of the idea behind the picture in the brain. Any comments or questions about that? You kind of have to know that, know where we're going here. So now let me give you the details on what they actually did in this experiment. I would say of the three experiments on the test, your best possibility of getting a test question is going to come from this situation. So Lily is just coming back in. Can anybody highlight for Lily what the neuroanatomists have done for us here in the hippocampus? So we've kind of got on 417, information comes in through the perforant pathway, goes to the dentate gyrus, and then CA3 and CA1. The picture on 417 kind of shows that. CA3 is the corno-ammones, which if you're in neuroanatomy, you don't have anything better to do with your time, so you name things really weird that nobody could possibly understand because you don't have anything to do with your day. Not to belittle neuroanatomists at all. It's probably kind of an interesting field. So let's get to what they actually do in the study here. Okay, so phase one, they're not working with the animals here, they're working with what? They use rats, but what do they take from the rats here? What did I say they take from the rats here? Yeah, little cells. So they actually take slices of the hippocampus, they put it in a petri dish, and they do things to it. So you're not even working with an animal at this point in time. And what they basically do in phase one of this study, they put a small dose of electricity into the perforant pathway. They put a small dose of electricity in. Oh, looks like I have a typo up there. Sorry about that. A small dose of electricity in the perforant pathway. And then what they do is they measure the output postsynaptically. You could probably go for CA3 if you want. You see the little synapse there between the dentate gyrus and CA3? Do you see the little synapse in your book? If you put a little dose of electricity in, kind of a theme-based in the cognitive neuroscience class, Madison, you put a little bit of electricity in the perforant pathway, what do you think you find postsynaptically in the CA3 region?
You'll get a larger response.
But if it's trial one and it's a little bit in,
you'll probably get no response or very little.
Very little response. So trial one, a little in electrically, a little out. Now we're kind of talking electrophysiology. A little in, a little out. Seems pretty simple. What do you think they do in trial two? Follow the theme from the other studies. Stronger shock. Yes, they put a lot of electricity in. We actually have a name for it. It's on the board. What is that strong amount of electricity called? And your book actually has this as well. It's called tetanic stimulation. You put a lot of juice in here. High frequency electrical stimulation goes in. It's called tetanic stimulation. Tectonics, earthquakes, tectonic stimulation. You put a lot of electricity in. When you put a lot of electricity in to the perforant pathway and then you measure postsynaptically at CA3, what do you think you find? Hannah, what do you think you find?
A stronger reaction?
There you go. You put a lot of electricity in, you get a lot of electricity out. That's trial two. What do you think they do? Sam, can I ask you, what do you think they do in trial three?
They repeat trial one and put a little shock in.
Yes, they repeat trial one, and very importantly for your notes, they repeat trial one, and they can repeat trial one either right after doing this or even up to a couple of days later, even up to 4 days later. And what do you think they find when you just put this small dose of electricity in to the perforant pathway from either 1 to 4 days later?
They'll have a similar response to stage 2.
Bingo. You find a very similar response to phase 2. You'll have a strong electrical response. Now, does anybody know what we call electricity after the synapse? Let me give you the name of it. It's called an EPSP. It's called an EPSP. Does anybody know what the term EPSP means? EPSP stands for excitatory postsynaptic potential. You get a strong EPSP in phase 2 and phase 3. In CA3, you see a big EPSP, excitatory postsynaptic response. That's the large, I should have said that in phase 2, a large EPSP. Have people heard that term before or no? We're getting very neuroscience-y here, aren't we? A large EPSP. Any questions about that? So you see this going on, a large EPSP, and it turns out when you get the neurotransmitter in CA3, there's a neurotransmitter called glutamate. If you want to take this a step further, the neurotransmitter released in CA3 is glutamate. When it binds, glutamate causes what we know as a calcium influx. Does anybody know how calcium is charged as far as an ion? Is it positive? Is it negative? It's positively charged. It's got a charge of +2 on it. So when calcium comes in, what will happen postsynaptically? You'll have a lot of electricity, and this will cause this synapse to really be strengthened. That's why in phase 3, the little shock generates the big response. Does this sound very cognitive neuroscience oriented? It is. A lot of details here. The connection is strengthened here because glutamate is released, just like the serotonin in the other trial. When glutamate is released and binds postsynaptically, it allows, what did we say? A calcium influx, INFLUX. And calcium is positively charged, so it'll cause more action potentials, basically. So this is all very electrophysiological. So this is LTP. This is LTP. Long-term potentiation. Why is it called long-term potentiation? Where's the word long-term come from? Now we're going to kind of get at the meaning. Why is it called long-term? When on phase 3, when did we say you could put in that little mild electrical shock and still get the same response? Long term, because you can go into up to 4 days later and get the same thing going on. But this is an electrophysiological phenomenon. Any comments or questions? You guys understand? And the book should be useful as well, but the picture kind of works for us here.